Okay, here's a mysterious box. Looks like it came from China. Obviously something I ordered. All really taped up and lots of different colored tape. Let's see what this is. Okay. Try not to damage what's ever inside of it. Fun times here. Okay, gotta be careful when you use scissors like a knife, which is what I'm doing here. You don't want to put your fingers between the blades. I had it slip one time. That was not a good thing. The blades actually caught on something and pinched close on my fingers, and that was extremely painful. Oh, what the heck. Okay, read first. Because of the weight limit, a package cannot exceed 2.2 or 2 kilograms. So if it's divided into 2 packages for delivery, please remember to check and enjoy. Tracking numbers are okay. So I believe this is the Tesla coils that I ordered, and I don't know why they have a limit on package weight. Probably the criminal bureaucrats are getting involved there. So it looks like the aluminum toppers, which are these are pretty nice size aluminum toppers. I think I paid like $50 a piece for these coils, so that's going to be nice. That's a very nice spun aluminum topper, and I'll have to wait for the coil to come in. So I'm getting excited. I didn't think this was going to make it through the Corona fiasco. Because they're just doing, bureaucrats are doing all sorts of crooked things to try to force their injections upon us. And it's not going to be a vaccine, it's going to be some tracking device or something that kills you or something, because it's population control. So they're going to keep on punishing us with their bureaucratic nonsense until they kill us with their injections, I guess. Anyway, hopefully our other part of the coils will come soon. Okay. Okay, looks like it finally came, and I really mean that, because if this is what I think it has been a long time coming. It took forever. Okay, let's see what it is before I talk too much. Is it? Oh my god, it's my Tesla coils. See, the tops came like months ago, and they said they couldn't ship the bottoms with the tops because of the weight limit. What is this? It's like a frickin' brass rod. Okay. It looks like it has the secondary coils and the primary coils. Of course, I don't care too much about the primaries because that looks like that's easy to wind. This is something that would take a lot more effort to do. It looks like it's all varnished and everything. Read first. Use your phone, scan, or QR code, or type into the website into your browser to get the instructions. Enjoy. Okay. Very interesting. Okay, so it looks like I ordered 3 coils because I had a specific project in mind. I'm not sure what this brass rod is for, but they finally came, so I have the tops and the bottoms now. This is excellent. It's going to be so much fun. Okay. Okay, so it looks like they sent me this little do-it-yourself demo thing that I guess you can scan on your phone. Let's see if this works. Okay, oh look, it came up with a link. Let's see what this link. Come on. Got a link, I guess. Hands magic. Okay. Oh wow, yeah, well, that looks pretty simple. I just need to build this frickin' power supply, huh? Oh, come on. Oh, wow. Unless that power supply comes with it. I don't think anything looks simple about this. I got my own power supplies, though. Oh, I see. So that needle is for discharge. Okay, very interesting. I assume this stuff didn't come with it. First try, second try. Okay, anyway. So there's that. I think we'll do our own demo. Hands magic. Let me do my okay. Okay, I've gotten out all the parts that I've received. Or it took me forever to receive these other parts. I actually put my own screw in there for I was doing some other stuff, but maybe I'll have to take that screw out of the Corona cap. Okay. And here is our primary coil, which is something I could have made in a few minutes probably, but it's fine. I didn't buy it for that. And I guess from looking at their do-it-yourself thing, that this brass rod with a point on it is to make discharges off of the coil. And let's take a look at the coil in here. Okay, there's wire coming off this side. That's probably for the ground. And it looks like there's copper tape on the top up here. So I guess, oh come on. Let's just set these things. I'm going to put the primary down there and the secondary on the wire through the middle of the secondary. So it's nice around that. Okay, primary and secondary. And I don't know how this top fits on there. I guess it just sits on there like that, like it teeters on top. There's nothing to hold it in place. Whatever. Okay, so the top terminal just sits on top of this copper strip here, which I'm going to assume is hooked someplace to the end of the wire. I can't see the end of the wire because it's all been taped up. But I'm going to assume that that connects to the coil. And our discharge thing, there's no directions with this guy, right? There's our coil. Okay. And I built this power supply. I talk about in another video, the Evil Genius simple switching power supply. And we'll see if we can, this one's only good up to maybe a couple hundred kilohertz. And that's the bandwidth of this device, but maybe it's high enough to hit a resonant frequency on this coil. I'm going to try to find the resonant frequencies, and I'll tell them to you so you'll know what frequency this coil operates at. And I'm going to run the bottom coil unmatched, no capacitor on it, i.e. And when I find out what the resonant frequency is, I'll be able to calculate what kind of capacitance I need to match it. Okay? Should be interesting. Okay, so I made my own ground from I pulled a pin out of one of these power strips, the ground pin, and I just soldered it onto a wire, and I got some high voltage wire and put a clip lead on the other side. And so I'm going to plug this into, oh, come on. Oh. Anyway, here's our power strip, and there's really only one hole this can plug into, and that is, let me just plug it into this one down there. That's the ground hole there. And so now I can take this other side and connect it to the ground wire of the primary Tesla coil. Now I don't need to ground it. It could just produce high voltage out that side also, and that will change the resonant frequency. Resonant frequency will also be different when you put the cap on top here, right? Maybe it's supposed to sit like that. Okay, I guess it's supposed to sit upside down like that. That seems to fit pretty nicely on that little copper thing. I might have to take my extra screw out that I stuck in there. And we'll test it out with our little power supply that we built here. A little switching power supply I show in one of my other videos. Should be interesting. Okay, so here's a little trick I'm going to try before I hook it up to the power supply, because it was getting kind of hot and I didn't want to burn out the fat while I'm just searching around for the resonant frequency. So I have the clip leads in my hand, and I'm going to just put them kind of across the coil, not touching it though, because I don't want to burn these out. And what I'm going to do is I'm going to sweep the frequencies up here and just watch the scope here and see when it gets excited. And so if I go up and down, so that we're at 30 kilohertz, 40 kilohertz. Oh, see, looks like there's a resonance right there at about 52 kilohertz. Okay, so look up there. There's 52, I guess 54 kilohertz. We're getting some kind of response, and I think there's a little bit bigger response up around 90. Okay, so see, there's a stronger resonance right there, and that is okay around 90 kilohertz. So I think our power supply should be able to drive this. There's probably other resonances up higher. I mean, I could go up to, let's see, go up to the next range. Oh, stupid. Okay, so we're at the 100 kilohertz right now. And, oh, look at that. That's a really strong resonance right there. 268 kilohertz. So that might be the frequency that we want to operate at. That's probably the main resonance. Okay. And I'm going up, and there might be a little resonance there, but that's way high. That's like 800 kilohertz. So it looks like probably our main resonance is at right there. Look at that. 270 kilohertz, around there. Okay. So let's see if we can drive our coil at that frequency and get some power out of it. Should be interesting. Uh-oh. What happened? Okay, so here is our, our neon light, and I'm just driving it with my signal generator, and you can see the neon light is lighting up while I'm holding it close to the coil. 267 kilohertz. So that is definitely our resonance, and I believe our power supply can kind of supply power at that frequency. If I match the primary coil, it should be better too. Now let me do some calculations maybe, but definitely here. Let me turn off this light. Okay, there we go. There's our Tesla coil, and look at that. It's lighting up with my hand, just with the signal generator. Okay. Pretty good, huh? Okay, so here is our solid state Tesla coil. Let's see if I can do this. I'm going to hold this with my finger there, and I'm just going to touch the circuit here. And you can see as I'm touching the circuit, it is lighting up the neon light. So we are definitely getting power out of this thing. Let me just clip this thing on, I guess, and we'll run this coil continuously. See that? We're definitely getting high voltage out of this guy with our little circuit driver here. Okay, seems to be running pretty good. Let me unplug it and I'll see how hot the FET's getting. I don't have a heat sink on this guy. Yeah, it's getting kind of hot. It's probably going to need a heat sink. But it looks like our little evil genius ZIF connector power supply is able to drive our solid state Tesla coil. And I don't have the primary circuit matched either, so it should put out a lot more power when I match it with a capacitor of the right capacitance. I need to measure the inductance, and since we know the resonant frequency, 2.68 kilohertz, I guess we'll be able to calculate what kind of capacitance we need to drive this at resonance, and we should get a lot more power out of this guy then. Okay, should be interesting. Very interesting, huh? Definitely love Tesla coils. We'll build a time machine with this one. Okay. Okay, so let's just check the inductance of our primary coil so I can figure out what kind of capacitance we need for that. We have the resonance frequency, right? 267 kilohertz about, where this coil is really excited. When it's grounded, by the way, it'll have a different resonance frequency if you don't have the cap on and if it's not grounded, but with those conditions. And it looks like it is about 11.5 microhenries. Okay, so we need to do some calculations and see exactly what kind of capacitance we need to stick on this guy to match this, so it can be matched into our coil and we'll get more efficient input and higher power out of it. And again, I'm just running one car battery, and the FET is not heat sinked, so many improvements still. But I think we're making good progress. We've shown that our power supply, which I show in a different video, and the evil mad scientist, ZIF connector that I converted into a switching power supply, can in fact have enough bandwidth to drive our little Tesla coil that we got, $50 Tesla coil from China. Should be interesting. Okay. Okay, so what I did is I have my equation here. Let's just put the equation up. For the resonant frequency, 1 over 2 pi times the square root of the inductance times the capacitance. See, I have capacitance and inductance in these columns. So we know the inductance is 11.4 microhenries because we measured it on our handy dandy little scope over here, LRC meter. And so I started guessing at the capacitance. I could have done it the other way around, but I just had this formula in here. And it turns out about 30 picofarads gets us pretty close to the 270 kilohertz, right? Remember, we're at 268, 270, close enough. So 30 picofarads should get us there. So I'll have to see. Of course, when you're doing high frequency stuff like that, you want capacitors that have low losses, like doorknob capacitors may have a lot of losses when you try to run them at resonant frequencies like that. Mica capacitors would be better because they're lower loss, but we'll see what we got. And also polyurethane capacitor. You have to look at the loss tangent of the materials that you're using. Mica is definitely the best though, but they're expensive. Let me see what kind of capacitors I have around here. See if we can match our Tesla coil. Okay, so I have my neon light here. I don't know if you can see that very well. Oh, must have gone out. Okay, it's right there. And I have my tunable capacitor here hooked up near this coil. And I soldered the leads onto the primary. And so let's, I have the scope tuned in to the resonant frequency, which is about 284. And let me just, I'll turn off this light here, and I'll just start twiddling with the knob here, and see if we can bring this guy into resonance by twiddling. See, I can increase and decrease the power output here just by twiddling with this capacitor down here. Okay, I guess we're out of resonance now. Oh, what happened? Oh, our clip lead came off, that's why. I'm sorry. Yeah. Okay. Let me tune this guy back in. Okay, so there's our resonance. See, I can tune it in like so. He's just capacitively coupled to this coil, and then other lead is hooked to the ground of the coil. Okay, so we'll get the frequency tuned in, and then I'll twiddle with our capacitor down here, and see, I can improve the match or make the resonance go away, so we can get more power out of our coil by matching the primary and the input. Okay, see that? The LED is glowing, or the neon light is glowing a lot brighter now. And all I'm doing is I'm just twiddling the variable capacitor here. So anyway, very interesting, huh? I don't know what kind of voltage we can stick on those, but for low power solid state Tesla coils, it looks like this might be a good way to match the primary. Anyway, this is Dr. Janes, and thanks for watching.